So these more integration techniques, we have something called the integration by parts. This is solving in one pass. We have something called the multiple passes, still integration by parts, and solving for the unknown integral, integration by parts, integration by partial fractions. There we go. Integration by partial fraction. So it's interesting. You can integrate by a part of something, or you can integrate by a partial fraction of something. Integrating powers of sines and cosines. Secants and tangents. So we've introduced a few new things here. We introduced sine and cosine. I'm going to group those together because they're very related. And then we have secant and tangent. Although, there we go. That's better. So we have our sine and cosine and our secant and tangent. So we have integrating powers, integrating products, different angles. So we've introduced power integration, product integration, and angles. There's a bunch more here. Trigonometric substitution. What is trigonometric substitution? And if you're just joining us, when I say trigonometric substitution, you should be saying aloud or in your head trigonometric substitution. Don't just sit back and watch and not use this as an exercise tool. So like this next one, infinite limit. You can integrate over an infinite limit. So when I say infinite limit, you say great, infinite limit. Integrands, discontinuities. Ooh, sounds interesting. What is an integrand? What is a discontinuity? And here's a big one. Ordinary differential. Equation. So remember earlier we had different types of equations. We had there's an equation in here somewhere. Do you see it? Differential equation. So there's types of differential equations, and this one happens to be ordinary. Ordinary differential equation. And they're calling that ODE. Wow, what is this one? Solutions from slope fields and isoclines. Ooh, those are new ones. what is a slope field and what is an isocline? I say slope field, you say, I say isocline, you say, awesome. Solving separable first order differential equations. So see, we had the differential equation, and then we have an ordinary differential equation. Now we have the first order differential equation. And not only that, but there must be types of first order differential equations. There must be something called a separable first order differential equation. So it sounds like the first order differential equation can be separated into more than one thing, and then numerical methods for solving these. Now, did we get the numerical method concept? We got the Newton's method, but there must be a certain type of method that is numerical and not non-numerical. So let's go ahead and add that. Numerical method. And I don't know what other types of methods there are. Alright, so now we're on to sequences and series. Now we're running out of room here. So what I'm going to do is I'm going to go ahead and take these guys, move them down, move him up, move somebody somewhere else here. Let's go ahead and move these guys over here, including this linear function model. There we go. Now we're back in business. And again, if you're just joining us or you skipped forward, what we're doing here is we're examining the calculus concepts. And we're going to find out how many we discovered here shortly. But now we're on to sequences and series. That's quite a different word here. So we have what is a sequence and a series. And then they have their own limits and convergence. Ooh, that's a new one. Convergence. Then we have, looks like we have some kind of tools to determine convergence. Tools are pretty generic, so I'm not going to record those. Introduction to infinite series. Okay, so there's series. Guessing again, there's different types of series. In this case, infinite series. And then we have some properties of those. Positive term series, the integral test. Okay, so anything with a test on it sounds important. Integral test. And what is this positive term series? Another type of series. Now they're saying there's the integral test and the comparison test. So that's good to know. There's two tests here. One to compare and one to, I don't know, integrate possibly. PT series, so that must be corresponding to positive term series. Ratio and root test for convergence. Alright, so we have two more tests. We have a ratio test. Now these are testing for convergence, which we have up here. And we have the root test for convergence. I'm guessing these tests can be used for other things as well. Maybe not, but we will leave out the word convergence because we already have it here. Positive and negative terms. Alternating series. Oh, and here's another type of series. Put it right next to this one. Alternating. Wonder what that means. Alternating series. Positive term and negative term. Those are pretty generic too, so we'll leave those alone. Positive and negative term series. Oh, but now it's a type of series. Absolute and conditional convergence. Alright, so convergence came up again, so let's do, must be different types of convergence. There must be something called an absolute convergence and a conditional convergence. And there must be another type of series called the positive. Oh, we have that one. We have the positive term series here, but we didn't actually have the negative term series. There we go. And then we have the ratio and root tests for absolute convergence. We got that one. And there's a bunch of convergence tests. Okay, so we didn't get the actual concept of a convergence test. There we go. There's probably more that's not listed here. Power series. Okay, so another type of series. It's fine. And they're just introducing it, and they're talking about convergence again. Function representation and operations related to the power series. You know what? Let's get this representation concept down. What does function representation entail? Okay, here we go. We have more series. We have a Taylor series and a Maclaurin series. So you can quickly tell that lots of series. Taylor series, Maclaurin series. And then we have, again, Taylor polynomials and Maclaurin polynomials. So Taylor and Maclaurin, we're doing quite a bit of work, sounds like. Taylor polynomial, Maclaurin polynomial. There we go. And if you don't know what the polynomial is versus the exponential, we might add these over here if we have some space. Taylor series, Taylor polynomial. Maclaurin series, Maclaurin polynomial. Series, truncation error. So there must be some errors that occur sometimes when dealing with a series. And there's probably lots of types of errors. In this case, it's a truncation error. Now, it looks like centers seems to be important. Taylor series calculation. There's calculations everywhere, so I'm not going to write that one down. But centers, choosing a center. Why is center so important? Binomial fractional power, integrals, differential equations. Or if that means binomial fractional integrals and binomial differential equations. It's interesting. We'll go ahead and write one of those down. Binomial fractional powers. And if you miss a few concepts, that's fine. This is, for your benefit to learn something new. Ooh, now we're on to parametric equations and polar coordinates. And then that's it from this particular author. Oh, actually, there's one more. Vectors in the plane of calculus. But let's see how much we can put on this here. We have parametric equation. We have polar coordinates. Now, a polar coordinate is different from a non-polar coordinate. Plane curve. Didn't we already get a plane curve earlier? Area between two curves. Plane curve. So that's coming up again. Now we have circles and ellipses. Now that's something we should all know about. Circle, go ahead and write those down though, because they apply to many things. And you should know the difference between a circle and an ellipse. Parametric equations of conics, in this case a hyperbola. So what is a conic? And we had hyperbolic functions earlier, but we didn't actually have the root of that hyperbola. You might have heard hyperbole, but this is hyperbola. And then we have parabola. We're filling up our graph fast here. Parabola. Parametric forms. Differentiations come up again, but I think we need to add parametric form. Area in the plane. Area between two curves. We had area under I believe it was area under a curve. Area between two curves, and now we have area in the plane. Sounds important to distinguish that difference here. The length of a curve. There's just a bunch of parametric stuff here. Might have to have a part 3. But we have the area of the plane, parametric form, the length of a curve. Seems pretty simple to me, but maybe it's not. Length of a curve. Area of a surface of revolution. So we have area of a surface. Feels like calculus 3. I'm not sure. We have this revolution again. That popped up earlier. Revolution solid, look at that. So the area of the surface of revolution. And we have the volume of revolution. Polar graphs. Polar coordinate system. Now we have polar coordinate. But we have a polar coordinate system. Polar equations of conics. Polar equation. Polar graph. Polar form. Polar calculus. Area in the plane. Length of a curve. We have length of the curve, but I don't have area in a plane. Length of a curve, surface area, and volume of a revolution. Volume of revolution. Revolution solid. So it's coming up so much that I do want to add one more here. We'll call it volume revolution. Okay. Now this author actually has another topic called the vectors in the plane of calculus. There's a bunch here, so what we can do is we can make a part 3, and I'll summarize the parametric and polar topics and then add the vectors in the plane.